I just want to come back to one of the properties of this graph. We drew this last week, car rolling down a slope. Okay, so the gradient of the line is actually the change in y divided by the change in x. Please can you guys just note that down, and we will then go on to that. There is another way of writing this equation, particularly this part of the equation, with some terminology that we already know, using science symbols. See if you can think what that might be. I could just put on. Yeah. We've got a symbol that means changing already. Greek alphabet, which is triangle, and that actually means changing. So we can rewrite this equation. Triangle y, which we say is dy, triangle x, dx. So you can replace that change in with a symbol that we've used already for the calculations. You've got it off a piece of paper.
Yeah.
No, go on, James, read it out anyway.
Well, it's not something crucible means energy equals mc delta t.
Yeah, it was Q equals mc delta t. The energy equals mass times the specific heat capacity at delta t. That c, incidentally, is different from our other c, the E equals mc squared, because the c in E equals mc squared is the speed of light squared, not specific heat capacity. Anyway, that's by the by. So, we have an equation. The question is, how do we now go about finding these values? And that's what I want to... we need to work out a change in, and we can do that using the end results. One thing that we are now thinking of, though, with our graphs, is we're looking specifically at the line of best fits this time. So I'm going to get you guys to draw on your speed distance or distance time graph. And I want you guys to ignore the crosses. Now we've got a line of best fit in. The line of best fit is averaged out all our results. And we don't actually need to think now specifically about the crosses, about the specific plot points. We're only thinking about the line of best fit. Now to calculate this dx amount, change in x, we can take the end value. But actually we can take any value on the x-axis. Now, what's our units for time? Seconds. Yeah, what's the units for distance? Meters. Excellent. So, we're quite fortunate in this experiment because the x-axis, as our independent variable, is the one that we choose. Which generally means that the plot points on there, we can choose our plot points as well. So to find this change in x, we need to take a lower point and draw a line up to the line of best fit, and a higher point, and draw that line up to the line of best fit. So say that's 20, 40, 60, 80, 100. This distance is then our dx, change in x. And what is that distance? Let's see, Sam, what's the distance between 80 and 20? 60. Yeah, it is. To get to that figure, I mean, actually it's obvious for us because we know that you add 60 to 20, you get 80. But actually to get the 60 figure, if these were more complicated, you subtract the smaller number from the bigger number, and that gives you the 60. So in this instance, go on, Nicola.
Why did you put that line at 80?
Good question. It could actually, this line could actually be anywhere. We could do from 40 to 100, or we could do from 40 to 60, or we could do from 40 to 80.
And what determines that?
Just it's your choice.
Oh.
Generally, with the line of best fit, using something wider is a bit easier because it's easier to see on the graph. This kind of becomes a bit more obvious once you actually get to put pen to paper, because it's all in the clarity of doing it. But we could just as well use 20 to 40. Or 20 to 60 or 40
So you
to
could
60.
do 20 to 100 if you wanted.
You could do, yeah.
Would it give
You could even do,
zero?
you could even do, yeah, as Leslie suggested, you could do 0 to 100 if you wanted to.
So you could just it's up to you.
Yeah, it is.
So is it giving the results for that solution?
Yes. There is a reason for why it gives you the same results. So in this case, let's just write down our dx is dx is equal to 60. The next stage of the calculation, we've worked out dx, change in x. We now need to work out change in y for that change in x. So we have to take a horizontal line from where that meets the line of best fit, and also where that meets the line of best fit. And that gives us a value, say, y1 and y2, and that then becomes our dy. Now, can anybody tell me why then it doesn't matter how big or small your dx is?
Because your y will change depending on which axis you
Fantastic. Yeah, absolutely spot on. It's a ratio between the change of y and the change in x, and you change x and y changes. So the ratio actually always stays the same because this is a straight line. Now the reason we don't always take naught, the naught point and the end point, is actually because you can have lines of best fit that are straight in parts and change direction if speed changes, if it's a distance time graph. Or you can get to bits which curve and then straighten up. And actually you might want to find the gradient of the line of best fit at a particular point. So this is a more general way of doing it, rather than just taking naught and the end value. But you can do that on a straight, it's just a straight line graph. Okay, so dy, and just like we said with here, 80 minus 20 gives us our dx value, which we know is 60 actually, because we know we had 60 to 20. The same applies here, so change in y is actually the big number, y2, minus the small number, y1. And that will give you your dy value. Okay, now obviously I haven't got figures on my graph, but you guys have got figures on your distance time graph. Okay, so our first point, your numbers will be a little bit different to mine, but dx is equal to 60. Dy is equal to, for my example, 15. 60 what? What are the units for this 60? 60 seconds, yeah. And the units for the 15? Yeah, brilliant. Okay, so we have got units, even though it's changing, they do still have units. They're not unitless, these figures. Then we write the equation that we're going to use. Gradient is equal to dy over dx. And only then do we put the figures in. And make sure that you get your figures the right way around. So 50, for me, that's 15 divided by 60, which is equal to 1.25. So I hope you guys have all got at least a figure for your calculation. The next question, of course, is my final figure currently correct? Go on, Samantha, what do you think I'm missing? I've got a number, but what else do I need? Yeah, I need the units. Numbers got to be accompanied by units. At the moment, it could be 0.25 cars or 0.25 pence, or until we put the units in, we don't know. But Leslie, you've got a suggestion for units. Yeah, meters per second. Does that sound all right to everybody else? Does anybody know why it's meters per second? Yeah, it is. It's all to do with the equation. And actually, in a lot of cases, you can work out what the final things are just by looking at the equation. When you write units, if you're just doing the units, you put them in square brackets. So this equation is actually equal to y, which is measured in meters, over x, which is measured in seconds. And meters divided by seconds is just another way of saying meters per second. That is a measure of speed, and that is actually what our units are for our final. We can do meters / seconds, we can do meters seconds to the -1, that means all means the same thing.